The calendar reads November 15th, 2025. Across the northern hemisphere, temperatures drop. Frost forms on windows in Boston. Snow blankets the streets of Moscow. Londoners bundle up against the bitter wind. In Tokyo, commuters pull their coats tighter against the cold morning air. Winter approaches with its familiar cold grip, inexorable and predictable. Yet, in just 7 weeks, on January 4th, 2026, Earth will reach its closest point to the Sun for the entire year 147.1 million kilometers from our star, 3 million kilometers closer than in July's summer heat. The planet will be receiving approximately 7% more solar energy than it does at its farthest point in early July, when temperatures in the northern hemisphere soar and people seek shade from the blazing sun. Closer to the Sunday, in the dead of winter, this apparent paradox sits at the heart of one of astronomy's most elegant concepts, perihelion, from the Greek peri, near, and helios, sun. Perihelion marks the point where an orbiting object comes nearest to our star. It's a moment that defines orbital behavior, shapes planetary climates, governs the motion of asteroids and comets, and reveals the hidden nature of cosmic visitors from beyond our solar system. Right now, 270 million kilometers away, an ancient wanderer experiences the aftermath of its own perihelion passage. The comet designated 3I Atlas, the third confirmed interstellar object ever detected passing through our cosmic neighborhood, passed its closest approach to the Sun just 2 weeks ago, on October 29th. What happened at that moment transformed a frozen relic from another star system into one of the most debated and mysterious objects in modern astronomy. Space-based telescopes, watching from orbit, recorded something unexpected during those critical hours. 3I Atlas brightened explosively, twice as fast as normal comets typically brighten as they approach the Sunday. Its color shifted dramatically from reddish to blue, not just slightly blue, but distinctly bluer than the Sun itself, which should be physically impossible for a cold comet reflecting sunlight. Gases poured off its surface at rates that suggested billions of tons of material being released in a matter of weeks. The transformation was so dramatic, so sudden, so unlike anything predicted by standard cometary models, that scientists are still analysing the data, trying to understand what they witnessed. This is the story of perihelion told through two objects, separated by scale, composition, and origin, yet bound by identical physical laws. Earth, making its annual closest approach in the mundane rhythm of seasons that humanity has observed since the dawn of civilization, and 3I Atlas, experiencing its first and only perihelion in billions of years of existence. One passage, gentle and predictable, marked only by slightly shorter days of winter and imperceptible changes in solar energy. The other, violent and mysterious, marked by explosive outgassing and color changes that challenge scientific understanding, both governed by identical physical laws discovered centuries ago by mathematicians who could only dream of the cosmic visitors that would one day test their theories. The tale begins not with modern telescopes or space probes, but in a cold German city 4 centuries ago, where a brilliant mathematician with poor eyesight and chronic illness wrestled with the stubborn orbit of Mars. Searching for mathematical harmonies he believed God had written into the fabric of the cosmos. Prague, winter of 1600. Johannes Kepler, aged 29, arrives in the city to work for Tycho Brahe, the greatest observational astronomer of the age. Kepler is brilliant but poor, socially awkward, deeply religious, and obsessed with finding mathematical patterns in nature. He believes the universe is constructed according to geometric principles, that God is a mathematician, and that understanding celestial motions means reading the divine mind. Tycho possesses something invaluable to this quest: decades of precise measurements of planetary positions, data more accurate than any collected before in human history. For 20 years, from his observatory on the island of Hven, Tycho has measured the positions of planets against the background stars night after night, recording their movements with unprecedented precision using enormous instruments of his own design. Without telescopes which haven't been invented yet, Tycho has achieved measurements accurate to about 1 arc-minute, roughly the resolution limit of the human eye. But Tycho doesn't share easily. He's protective of his data, worried that his young assistant might eclipse his fame by discovering what the observations mean. Some historians believe he deliberately assigned Kepler the hardest problem in his dataset: determine the orbit of Mars. Mars refuses to cooperate with any simple model for over 1,000 years. Since the ancient Greeks developed geometric models of the heavens, astronomers have assumed celestial bodies move in perfect circles, the perfect shape, unblemished by beginning or end, appropriate for the eternal heavens. Circles had been gospel since Plato and Aristotle. Ptolemy built his Earth-centered model using circles within circles, epicycles. Copernicus, who placed the sun at the center of the solar system in 1543, still used circles. Everyone used circles. But Mars won't fit circles, no matter how many adjustments are made. Kepler spends years on the problem. He tries circle after circle, adding epicycles, circles moving on, circles adjusting their sizes, changing their speeds, modifying their orientations. He uses all the mathematical tools available to him: geometry, trigonometry, ratios, proportions. Every calculation is done by hand, filling pages upon pages with numbers, sines, cosines, tangents. No calculators exist, no computers, no spreadsheets, just pen, paper, mental arithmetic, and trigonometric tables he must look up manually. Each orbital calculation might take days or weeks of continuous computation. Nothing works perfectly. The circular orbits match Tycho's observations at some points, then drift off at others. The discrepancy is small, just 8 arc minutes, 8/60ths of a degree. To visualize this angle, hold a coin at arm's length. The coin's diameter spans about 1 degree. 8 arc minutes is roughly the width of a human hair held at arm's length, or about 1/8 of the coin's diameter viewed from across a large room. 8 arc minutes. Tiny, almost imperceptible. Most astronomers would dismiss such a small discrepancy as observational error, or accept it as close enough. The match between theory and observation is already better than any previous model achieved. Kepler doesn't dismiss it. He knows Tycho's observations are more accurate than 8 arc minutes. Tycho's instruments, his methodical observations, his decades of experience, these measurements are trustworthy. If the model predicts one position and Mars sits 8 arc minutes away consistently, the model is wrong. The universe doesn't approximate. It doesn't do close enough. There must be an exact mathematical description of Mars's motion, and if circles don't provide it, circles must be wrong. This is a radical thought. Abandoning circles means abandoning 1,000 years of astronomical tradition, means rejecting the perfection of circular motion, means accepting that the heavens might not be as geometrically pure as philosophers claimed. So Kepler abandons circles. What if planets move in ovals, in ellipses? An ellipse resembles a squashed circle, or an elongated oval. There's a simple way to draw one. Push 2 pins into a board, loop a piece of string around both pins, pull the string taut with a pencil point, then trace the shape while keeping the string taut at all times. The resulting curve is an ellipse. The 2 pin positions are called foci plural, of focus. The beautiful mathematical property of an ellipse is that for any point on the curve, the sum of distances to both foci remains constant. That's why the string method works. The string length stays the same, so distance to focus 1 plus distance to focus 2 must always equal the string length. Kepler places the Sun at one focus of Mars's elliptical orbit. The other focus sits empty, nothing there, just a mathematical point in space. As Mars orbits, it traces this elliptical path, sometimes closer to the Sun, when it's on the side of the ellipse nearer to the Sun's focus, sometimes farther when it's on the opposite side, but always following the ellipse's curve precisely. When Kepler calculates Mars's orbit as an ellipse, with the Sun at one focus, something magical happens. Years of Tycho's observations fall into place, perfectly. Every measurement Tycho made, across multiple oppositions of Mars spanning decades, aligns exactly with this elliptical path. The error drops from 8 arc minutes to essentially 0, to within the measurement uncertainty of even Tycho's exquisite observations. It works. After years of frustration, after thousands of calculations, after rejecting the circular orthodoxy of a millennium, Kepler has found the answer. Planetary orbits are ellipses. In 1609, Kepler publishes Astronomia Nova, New Astronomy, announcing his revolutionary discovery. The orbit of every planet is an ellipse with the Sun at one of the two foci. This becomes known as Kepler's first law of planetary motion. It's revolutionary. It's heretical to some. It overturns 1,000 years of circular orthodoxy. Aristotle said circles. Ptolemy said circles. Copernicus said circles. They were all wrong. Kepler said ellipses, and he was right. But Kepler notices something else during his years of calculations, something subtle about how Mars moves along this ellipse. Planets don't travel at constant speed along their elliptical paths. When closer to the Sun, they race forward quickly. When farther away, they crawl along slowly. The speed continuously varies throughout the orbit. How much faster or slower? Kepler discovers a precise mathematical relationship describing this speed variation. Imagine drawing a line from the Sun to a planet, like an invisible spoke connecting the hub to a wheel's rim. As the planet moves along its orbit, this line sweeps out an area like the hand of a clock sweeping across the clock face, or like a searchlight beam sweeping across the ground. When the planet is near the Sun and moving fast, the line is short but sweeps quickly. When the planet is far from the Sun and moving slowly, the line is long but sweeps slowly. Kepler discovers that despite these varying speeds and distances, this line sweeps out equal areas in equal times, no matter where the planet is in its orbit. If you mark any 2 points on the planet's orbit such that the planet takes exactly 1 week to travel between them, and draw the area enclosed by the Sun, the orbital path, and the two radius lines, that area will be identical to the area swept during any other week-long interval anywhere else in the orbit. This becomes Kepler's second law. A line joining a planet, and the Sun sweeps out equal areas during equal intervals of time. The implications are profound. Though Kepler doesn't fully understand why this law works, that understanding awaits Isaac Newton 80 years in the future. Consider Earth at perihelion in January versus aphelion, the farthest point from the Sun, in July. Draw that imaginary line from the Sun to Earth. Now let 1 week pass and draw the line again. The area swept out in that week must equal the area swept during any other week of the year. At perihelion in January, Earth sits closer to the Sun, so the imaginary line connecting them is shorter, about 147.1 million kilometers. For this shorter line to sweep out the same area in 1 week as it would in July, when the line is longer, Earth must travel through a larger angle around the Sunday. Travelling through a larger angle means covering a longer arc length along the orbit. Covering longer distance in the same time means faster speed. At aphelion in July, the line is longer about 152.1 million kilometers. To sweep the same area in 1 week with this longer line, Earth needs to travel through a smaller angle, covering shorter arc length along its orbit. Shorter distance in the same time means slower speed. The numbers bear this out precisely. At perihelion in early January, Earth cruises along at about 30.29 kilometers per second. That's 108,900 kilometers per hour, or 67,700 miles per hour. At aphelion in early July, Earth slows to about 29.29 kilometers per second, roughly 1 kilometer per second slower, a difference of about 3.4%. That might not sound dramatic, a 3.4% speed change. But this speed variation has real, measurable consequences that humans have observed for millennia without understanding the cause. This explains why seasons have different lengths. Northern winter, measured from the December solstice to the March equinox, lasts about 89 days. Northern spring, from March equinox to June solstice, lasts about 93 days. Northern summer, from June solstice to September equinox, stretches to about 94 days. Northern autumn, from September equinox back to December solstice, takes about 89 days. Winter and autumn together last 178 days. Spring and summer together last 187 days. Summer half of the year is 9 days longer than winter half. Why? Because Earth moves faster during northern winter when it's near perihelion. The planet zips through the winter portion of its orbit more quickly. Earth moves slower during northern summer when it's near aphelion, so summer drags on longer. The asymmetry of seasons, something farmers and calendar makers noticed long before Kepler, emerges directly from perihelion and aphelion, affecting Earth's orbital speed. 10 years after discovering his first two laws, Kepler discovers a third relationship, one he considers his greatest achievement because it reveals a deeper mathematical harmony in the solar system. Kepler's third law reveals a connection between how far a planet orbits from the Sun and how long it takes to complete one orbit. The relationship is precise and beautiful. The square of a planet's orbital period is proportional to the cube of its average distance from the Sunday. Written as an equation, t square is proportional to a cubed, where t is the orbital period, time for one complete orbit, usually measured in years, and a is the semi-major axis, half the long diameter of the elliptical orbit, essentially the average distance from the Sun, measured in astronomical units, where 1 AU equals Earth's average distance. This law allows astronomers to calculate how long any orbit takes if they know the distance, or vice versa. The relationship holds with stunning precision across the entire solar system. For Earth, the math is simple because we defined our units based on Earth. A equals 1 AU and t equals 1 year. So t square equals 1, squared equals 1, and a cubed equals 1, cubed equals 1. The relationship holds, 1 equals 1. For Mars, orbiting at an average distance of about 1.524 AU proportion to t, square equals 1.524 to the power of 3 equals 3.54, so t equals square root of 3, 54 equals 1.88 years. Mars takes about 1.88 Earth years, or roughly 687 Earth days, to complete one orbit. Check any astronomical table, and that's exactly right. For Jupiter at 5.2 AU proportion to t square equals 5.2 to the power of 3 equals 140.6. So t equals square root of 140, 6 equals 11.9 years. Jupiter takes about 11.9 Earth years per orbit. Again, precisely correct. For Neptune at about 30 AU proportion to t, square equals 30 to the power of 3 equals 27,000, so t equals square root of 27,000 equals 164 years. Neptune requires 164 Earth years to complete one orbit around the Sunday. The relationship holds across the entire solar system with exquisite precision. Kepler considered this third law his greatest triumph. He believed it revealed the fundamental harmonic structure of the cosmos, the mathematical music of the spheres made manifest in the relationship between distance and time. He was convinced this was proof of God's geometric design of the universe. Whether one shares Kepler's theological interpretation or not, the mathematical beauty is undeniable. 3 laws, elliptical orbits, equal areas and equal times, and the relationship between period and distance together describe planetary motion with perfect accuracy. These laws predicted where planets would be years or centuries in advance. They worked for every planet known in Kepler's time, and when new planets were discovered later, Uranus in 1781, Neptune in 1846, Pluto in 1930, Kepler's laws described their motions exactly. But Kepler didn't know why any of this worked. He had no concept of gravity. That revolutionary insight awaited Isaac Newton in the 1680s. Kepler didn't understand forces, energy, or momentum. His laws described what planets do they move in ellipses, sweep equal areas in equal times, follow the period-distance relationship, but not why they do it. They were empirical laws, derived from observation and geometric analysis, not from understanding the underlying physical cause. The why would require understanding forces, energy, and the universal law of gravitation. But before exploring that deeper understanding, the story shifts forward in time and outward in space, to an object that spent an incomprehensible duration in the darkness between stars, waiting for its moment in the sun's light. Somewhere in the Milky Way galaxy, at coordinates unknown to us, roughly 8 to 10 billion years ago, more than twice the age of our solar system, a star formed from a collapsing cloud of gas and dust. This molecular cloud, perhaps light years across, contained mostly hydrogen and helium left over from the Big Bang, but also heavier elements: oxygen, carbon, nitrogen, silicon, iron, and others. These heavier elements, which astronomers call metals, even though they include non-metallic elements, like oxygen, were created inside previous generations of stars and scattered through space when those stars died in supernova explosions. As the cloud collapsed under its own gravity, it began to spin faster due to conservation of angular momentum, eventually flattening into a disk, a protoplanetary disk, with a growing star forming at the center, where material accumulated most densely. This is the standard picture of star formation, the process that created our Sun 4.6 billion years ago. This same process created the star that would become the parent of 3I Atlas billions of years earlier. Within this protoplanetary disk around the nascent star, the process of planet formation began. Initially, the disk contained tiny dust grains particles, smaller than smoke particles, perhaps a micrometer, 1/1,000,000th of a meter across, made of silicates, rocky minerals, carbonaceous material, and in the colder outer regions of the disk, various ices. These dust grains collided frequently as they orbited the young star. When collisions were gentle, van der Waals forces, weak attractive forces between molecules, made particles stick together, slowly growing larger. Micron-sized dust grains became millimeter-sized pebbles. Pebbles accumulated into centimeter-sized rocks. This growth process is straightforward in principle, but remarkably complex in detail. In the cold outer reaches of this protoplanetary disk, beyond what astronomers call the CO2 ice line, the distance from the star where temperatures drop low enough, below about 195 Kelvin, or -78 degrees Celsius, for carbon dioxide to freeze solid, a small body began to grow. This region was far from the star, perhaps 5 to 10 times farther out than Earth's equivalent distance, where temperatures remained perpetually frigid. The growing body accumulated material slowly over hundreds of thousands or millions of years. Dust grains stuck together, pebbles merged, boulders combined. Eventually, through collisions and gravitational attraction, a comet formed a few kilometers across, made of ices frozen from the nebula gas, carbon dioxide, CO2, water, H2O, carbon monoxide, co-methane, CH4, ammonia, NH3, and various other volatile compounds, all mixed with rocky and carbonaceous material that formed at higher temperatures and drifted outward through the disk. This comet, the object that would eventually become 3I Atlas billions of years later, was unremarkable among the countless trillions of similar bodies forming throughout the galaxy during this epoch. It orbited its parent star in the frigid outer regions, probably 10 to 50 AU from the star, if its system was structured similarly to ours, in the region analogous to our Kuiper belt or Oort cloud. For millions of years, perhaps hundreds of millions of years, the comet remained in this stable orbit. It gradually accumulated a surface crust of organic compounds, as cosmic rays, high-energy particles, mostly protons, flying through the galaxy at near light speeds bombarded its surface. Each cosmic ray collision broke chemical bonds, created free radicals, and drove chemical reactions that slowly built complex organic molecules called tholins. These tholins, dark, reddish-brown substances similar to those found on Pluto, Saturn's moon Titan, and other cold outer solar system bodies, accumulated in a layer perhaps centimeters to meters thick on the comet's surface. Then, something changed the comet's fate. Perhaps a giant planet in that system underwent migration, a process now recognized as common during planetary system evolution. Giant planets don't necessarily form in their final locations. They interact with the gaseous protoplanetary disk, with other planets, and with smaller bodies, causing their orbits to change over time. When Jupiter or Saturn-mass planets migrate, they gravitationally stir up everything around them, scattering smaller bodies like comets and asteroids. Perhaps the comet had a close gravitational encounter with a giant planet. When a small body passes close to a massive planet, the planet's gravity can dramatically alter the small body's trajectory. If the geometry is right, the planet can accelerate the small body to extremely high velocity high enough to exceed the star's escape velocity. Perhaps gravitational perturbations from a passing star disrupted the outer regions of the planetary system. Stars don't form in isolation. They form in stellar nurseries containing hundreds or thousands of young stars relatively close together. During the first few million years, before stars drift apart, close encounters between stars are common. Such encounters can gravitationally disturb the outer regions of planetary systems, ejecting comets and asteroids. Whatever the specific mechanism, planetary migration, planet encounter, stellar flyby, or some combination 3I Atlas was accelerated to high velocity. The comet's speed increased to roughly 26 kilometers per second relative to its parent star, exceeding the star's escape velocity of perhaps 20 to 25 kilometers per second, depending on the star's mass and the comet's distance. The comet was ejected from its home system, cast into interstellar space, becoming one of countless trillions of orphaned bodies wandering the galaxy. For billions of years, perhaps 5 billion, perhaps 8 billion, perhaps even longer, 3I Atlas wandered through interstellar space. It drifted through vast regions of emptiness, occasionally passing through diffuse clouds of interstellar gas containing only a few atoms per cubic centimeter. It tumbled slowly, its rotation rate determined by whatever last collision or near miss it experienced before ejection. Its temperature, equilibrated with the cosmic microwave background radiation, the faint afterglow of the Big Bang that permeates all of space. At interstellar distances from any star, temperatures drop to just a few degrees above absolute zero, roughly 2.7 Kelvin, negative 270.4 degrees Celsius. At these temperatures, essentially everything that can freeze is frozen solid. Water ice, CO2 ice, CO ice, nitrogen ice, methane ice, all locked together in an ultra-deep freeze that would persist for billions of years. Cosmic rays continued to bombard the comet's surface. Each collision deposited energy, broke chemical bonds, created exotic molecules that wouldn't form under normal conditions. Over billions of years, the surface became heavily processed, irradiated, darkened, chemically altered. The original pristine ices that condensed from the protoplanetary disk were covered by an irradiation crust, centimeters or meters thick, composed of complex organic molecules, freed radicals, and radiation-damaged ice structures. The comet travelled hundreds or thousands of light years during its journey. It may have made one or more orbits around the Milky Way galaxy's centre, taking roughly 225 million years per galactic orbit. It may have been ejected from the galactic disk into the halo and eventually fallen back. Its trajectory through the galaxy was determined by gravity, the combined gravitational field of all the stars, gas clouds, and dark matter in the Milky Way. At some point during this eon-long journey, purely by chance, 3I Atlas's trajectory intersected with another stellar system, ours. The probability of any specific interstellar object encountering any specific star system is extraordinarily low. Space is vast and stars are separated by light years. But with trillions upon trillions of ejected objects wandering the galaxy over billions of years, occasional encounters are inevitable. As 3I Atlas entered the outer reaches of our solar system, moving at 26 kilometers per second relative to the Sun, the Sun's gravity began to affect its trajectory. The comet's path started to curve, bending toward the Sunday. The object that had been frozen and dormant for billions of years was about to experience something it hadn't experienced since it left its home star system: significant heating from a star. And humans, with their telescopes and spectrographs, were about to detect it. July 1st, 2025, 5:15 a.m. local time. The Atacama Desert in Chile is one of the driest places on Earth, receiving less than a millimeter of rainfall per year in some areas. The extreme dryness, high altitude, 2,600 meters elevation, and distance from light pollution make it one of the world's premier locations for astronomical observations. On this particular morning, most of humanity is asleep, but on a mountain ridge in the Atacama, a robotic telescope is wide awake. The Atlas Asteroid Terrestrial Impact Last Alert System telescope is part of NASA's Planetary Defense Program, specifically designed to find potentially dangerous asteroids that might threaten Earth. It consists of 4 robotic telescopes stationed around the world, 2 in Hawaii, 1 in Chile, and 1 in South Africa. Each telescope scans huge swaths of sky every clear night, taking multiple images of the same regions and using computer algorithms to detect anything that moves between frames, the signature of asteroids, comets, or any solar system object moving against the background of distant stars. Between 5:15 a.m. and 6:20 a.m., the Chilean Atlas telescope captures 4 separate images of a faint object at coordinates 18 hours 07 minutes 27.68 seconds in right ascension and -18 degrees 41 minutes 40.2 seconds in declination. The object appears at magnitude 17.5, far too faint to see with the naked eye, invisible to binoculars, requiring at least an 8-inch telescope and a good camera to detect. The software that automatically analyzes Atlas data flags this object as potentially interesting. Its motion is unusual, it's moving at an angle and speed that don't match the expected behavior of main belt asteroids or typical comets. Main belt asteroids between Mars and Jupiter move in predictable patterns against the background stars. This object's motion doesn't fit those patterns. The discovery is immediately reported to the Minor Planet Center at the Smithsonian Astrophysical Observatory in Cambridge, Massachusetts, the official international clearinghouse for all observations of asteroids and comets. Professional and amateur astronomers worldwide check the Minor Planet Center's listings daily to see what new objects have been discovered. Within hours of the initial detection, something extraordinary happens. Astronomers around the world start searching archival data images taken in previous weeks that hadn't been carefully analysed yet for moving objects. They find 3I Atlas in older images. The comet had actually been photographed as early as June 14, 2025, by the Zwicky Transient Facility at Palomar Observatory in California. It was there in the data all along, captured by multiple telescopes, but nobody had noticed it because it was so faint and because nobody was specifically looking for it. These pre-discovery observations are incredibly valuable. They extend the baseline of observations back nearly 3 weeks before the official discovery. With observations spanning almost 3 weeks instead of just a few hours, astronomers can calculate the object's orbit much more precisely. The longer the observation baseline, the more accurately orbital parameters can be determined. And what that orbit revealed was absolutely stunning. When astronomers calculate an asteroid or comet's orbit, they determine several key parameters. One of the most important is orbital eccentricity, usually denoted by the letter E. Eccentricity describes the shape of the orbit. An eccentricity of E equals 0 means a perfect circle. An eccentricity between 0 and 1, for example, 0.2, 0.5, 0.9, means an ellipse. The closer to 0, the more circular. The closer to 1, the more elongated. An eccentricity of exactly 1 means a parabola. The object is travelling at exactly the sun's escape velocity. An eccentricity greater than 1, for example, 1.2, 2, 6.1, means a hyperbola. The object is travelling faster than escape velocity and is not gravitationally bound to the sun. For reference, Earth's orbital eccentricity is 0.0167, nearly circular. Mercury has the most eccentric planetary orbit at 0.206. Most comets from the Oort cloud have eccentricities around 0.995, extremely elongated ellipses that come close to the Sun, then retreat to thousands of AU distance. When scientists calculated 3I Atlas's eccentricity, they got a number around 6.1 to 6.2. That's way over 1. This object is moving so fast, approximately 61 kilometers per second at its closest approach to the Sun, that the Sun's gravity cannot hold it. It's just passing through our solar system on a hyperbolic trajectory, and once it leaves, it will never return. It will escape back into interstellar space and continue wandering the galaxy. But here's what sealed the identification as an interstellar visitor. When scientists trace a hyperbolic orbit backward in time, they can determine where the object came from. For objects that formed in our solar system, even those on highly eccentric orbits that barely remain gravitationally bound when traced backward, they still came from somewhere within the Sun's gravitational influence, from the Oort cloud or Kuiper belt or scattered disk. But when scientists traced 3I Atlas backward, the trajectory pointed outside from interstellar space, from the space between stars, from somewhere else in the galaxy. The object's velocity vector, when extrapolated backward before the Sun's gravity significantly bent its path, pointed toward a region of sky in the constellation Triangulum, suggesting it came from the direction of stars in the galactic thick disk, an older population of stars orbiting the Milky Way's center. On July 2nd, 2025, just one day after the initial detection, the Minor Planet Center made it official. They issued a public announcement confirming that the object designated C 2025N1 Atlas was an interstellar visitor, only the third confirmed interstellar object ever detected passing through our solar system, after 1I, Oumuamua, discovered in October 2017, and 2I Borisov, discovered in August 2019. The designation 3I Atlas encodes several pieces of information. 3I means it's the third interstellar object, I officially standing for interstellar in the designation system. Atlas honors the survey system that discovered it. It's traditional in astronomy to name comets after their discoverers, and since Atlas is a robotic survey rather than an individual person, the survey itself receives the honor within minutes. Of the announcement, astronomers worldwide began scrambling for telescope time. Interstellar objects are extraordinarily rare, 3 confirmed visitors in all of human history up to that point. And time is critically limited because these objects are moving at tens of thousands of miles per hour. Soon they'll be too far away, too faint, moving too fast against the background stars for effective detailed study. David Jewett and Jane Liu, 2 legendary planetary scientists at UCLA who've been studying comets and Kuiper Belt objects for decades, immediately requested urgent observations with the Nordic Optical Telescope in Spain. When their images came through on July 2nd, just hours after the interstellar confirmation, they saw something that filled them with excitement. 3I Atlas wasn't just a point of light. It had a diffuse, fuzzy appearance around the central nucleus, what astronomers call a coma. This meant the object was active. It was releasing gas and dust as it warmed, up approaching the Sunday. This was immediately important because the first interstellar visitor, Oumuamua, showed no obvious cometary activity. It looked like a bare asteroid or rocky body, just a point of light tumbling through space. No visible coma, no tail, no detectable outgassing. This led to years of intense debate about what Oumuamua actually was. Some scientists argued it was an asteroid, a rocky body. Others suggested it might be made of exotic ices, like frozen nitrogen or hydrogen, that sublime without producing visible dust. Harvard astronomer Avi Loeb even proposed it might be an artificial object, perhaps a light sail from an extraterrestrial civilization, based on its unusual acceleration and shape. But 3I Atlas? From the very beginning, from the first images just one day after discovery, it looked like a comet. A classic dirty snowball from space, ice and dust mixed together, warming up and releasing gas and dust as solar radiation heated its surface. At the Instituto de Astrofísica de Canarias in Spain, a team using the 2-meter twin telescope at Teide Observatory confirmed the cometary activity on July 2nd, the same day as the interstellar confirmation. In Arizona, astronomers at Lowell Observatory trained their 4.3-meter Discovery Channel telescope on the visitor. In Chile, the massive 8.2-meter Gemini South telescope began observations. Perhaps most excitingly, within just a few days, NASA's Hubble Space Telescope was retargeted to observe 3I Atlas. The space-based observatory, free from the blurring effects of Earth's atmosphere, could see details that ground-based telescopes couldn't match. Hubble's sharp vision would reveal the comet's coma structure, potentially detect jets of material flowing from specific active regions on the nucleus, measure the dust particle sizes from how they scatter light, and provide the highest resolution images possible of this ancient visitor. Astronomers knew that 3I Atlas was particularly special compared to the previous 2 interstellar visitors, and the reason had to do with timing. When Oumuamua was discovered in October 2017, it was already on its way out of the solar system. It had passed its closest point to the Sun, PERIHELION, on September 9, 2017, about 6 weeks before discovery. Astronomers only had about 80 days total to study it before it became too faint and too far away to observe effectively. It was like catching a glimpse of a mysterious stranger who was already walking away down the street, nearly out of sight. 2I Borisov, discovered in August 2019 by amateur astronomer Gennady Borisov using a 65cm telescope he built himself, was better. It was spotted about 3 months before its perihelion passage in December 2019, giving scientists several months to study it on the way in and several more months as it departed. The longer observation window allowed detailed spectroscopy, composition measurements, and monitoring of how the comet's activity changed as it approached and then receded from the Sunday. But 3I Atlas offered something unprecedented. It was discovered in early July 2025, a full 4 months before its perihelion passage on October 29, 2025. This meant scientists had the entire inbound journey to study how the comet changed as it approached the Sun, watching it wake up from its billions-year hibernation, monitoring the increase in activity, measuring how gas production rates climbed, observing how the coma expanded and the tail developed. Even better, after perihelion, 3I Atlas would make its closest approach to Earth on December 19, 2025, at a distance of about 270 million kilometers, 1.8 AU. This gave scientists another opportunity for detailed observations as it headed back out into the cold, now fully active and bright from its perihelion heating. This extended observation window July discovery, October perihelion, December closest Earth approach was a gift to science. Every additional day of observations provided more data, more precision in orbit determination, more opportunities to measure the comet's composition, and more chances to solve the mysteries it would inevitably present. At discovery on July 1st, 3I Atlas sat about 670 million kilometers from the Sun, approximately 4.5 AU, somewhere between the orbits of Mars and Jupiter. Even at that distance, where temperatures hover around -150 degrees Celsius to -100 degrees Celsius, the comet already showed that diffuse coma. This activity at such a large distance told scientists something important. 3I Atlas contained extremely volatile ices substances that vaporize at very low temperatures. Different ices sublimate turn directly from solid to gas without melting at different temperatures. Water ice begins sublimating noticeably when comets reach about 3 AU from the Sun, where temperatures rise above -150 degrees Celsius or so. But carbon dioxide ice can sublimate at much lower temperatures, around -195 degrees Celsius to -180 degrees Celsius. Carbon monoxide is even more volatile, sublimating at temperatures as low as -205 degrees Celsius. The fact that 3I Atlas showed activity at 4.5 AU suggested it contained these super volatile ices, particularly CO2 and CO. As July turned into August, 3I Atlas continued its inbound journey, moving roughly 5 million kilometers closer to the Sun each day. With each passing day, more sunlight hit its surface. More heat penetrated the icy exterior. More gas began flowing from the surface. The coma grew larger and brighter. On July 21st, 2025, Hubble Space Telescope captured its first detailed images of 3I Atlas when the comet was 277 million miles, about 446 million kilometers from Earth. Hubble's sharp vision revealed a teardrop-shaped coma, a bright central concentration of gas and dust with a diffuse envelope extending outward. The images showed the comet releasing dust particles at high speed, creating that classic cometary appearance that astronomers have studied for centuries. Interestingly, these early Hubble images also revealed something subtle: a faint, broad tail extending in a direction that appeared to point toward the Sun rather than away from it. This is what's called an anti-tail or sunward tail, and it's actually an optical illusion caused by viewing geometry. The real tail extends away from the Sun, pushed by solar radiation pressure on dust particles. But when observers see the comet from certain angles, particularly when Earth crosses the comet's orbital plane, perspective makes it appear that part of the tail points sunward. It's similar to how railroad tracks appear to converge in the distance, even though they're parallel. On August 6, 2025, the James Webb Space Telescope humanity's most powerful space observatory, orbiting at the L2 Lagrange point 1.5 million kilometers from Earth, turned its near-infrared spectrograph toward 3I Atlas. Webb was specifically designed to study the infrared universe, and many molecules important in comets have strong spectral signatures in the infrared wavelengths where Webb observes. Spectroscopy works by splitting light into its component wavelengths, like a prism splitting white light into a rainbow. But instead of just seeing colours, astronomers see dark absorption lines and bright emission lines at specific wavelengths. Every chemical element and molecule has a unique fingerprint in light-specific wavelengths, where it absorbs or emits photons due to quantum mechanical energy level transitions. Hydrogen absorbs and emits at different wavelengths than oxygen, which differs from carbon, which differs from water, which differs from carbon dioxide, and so on. By carefully analysing which wavelengths are present or absent in 3I Atlas's spectrum, astronomers can determine exactly what molecules are flowing off the comet's surface and in what quantities. When the Webb data came back and researchers at NASA Goddard Space Flight Center and other institutions analysed it, they found something remarkable. 3I Atlas was absolutely dominated by carbon dioxide. The CO-TWO to water ratio was approximately 8:1, 8 times more CO2 than H2O by number of molecules detected. This is one of the highest CO-TWO to water ratios ever measured in any comet. To understand why this is significant requires understanding how comets form in protoplanetary disks. In the disk of gas and dust around a young star, different ices condense at different distances depending on temperature. Close to the star where it's warm, no ices can form, everything is vaporized or molten. Farther out where temperatures drop, water ice becomes stable. This distance is called the snow line or frost line, typically around 3 to 5 AU in solar-type stars. But different molecules require different temperatures to freeze. Water ice is relatively stable and can exist at warmer temperatures. It condenses when temperatures drop below 273 Kelvin 0 degrees Celsius or 32 degrees Fahrenheit. Carbon dioxide ice requires much colder conditions. It only becomes stable below about 195 Kelvin, negative 78 degrees Celsius, or negative 109 degrees Fahrenheit. In a protoplanetary disk, this means CO2 ice only condenses beyond a certain distance where temperatures are low enough farther out than the water ice line. The fact that 3I Atlas is so rich in CO2 relative to water suggests it formed far from its parent star, well beyond that star's CO2 ice line, in the cold outer reaches of its home planetary system. It's a deep freeze object, a relic from the distant periphery of another star's family, from a region analogous to our Kuiper belt or scattered disk, but possibly even colder. This composition told scientists something profound. 3I Atlas's home system probably had different chemistry than ours, or 3I Atlas formed in a colder region than most solar system comets. Either the parent star was different, perhaps lower mass, creating a colder disk, or the disk chemistry was different, perhaps different abundances of carbon and oxygen, or 3I Atlas simply came from farther out in its system than most of our comets come from. Then, on August 21st, 2025, came an even stranger discovery. Astronomers Rohan Rahatgaonkar and Thomas Puzier, using the Very Large Telescope VLT in Chile, were analysing high-resolution spectra of 3I Atlas when they detected something completely unexpected: nickel vapor. Let that sink in for a moment. Nickel, a metal, vaporizing around a comet. Nickel's melting point is 1,455 degrees Celsius, 2,651 degrees Fahrenheit. For nickel to exist as a vapor, a gas, it needs to be heated to over 2,900 degrees Celsius, 5,250 degrees Fahrenheit. That's hot enough to melt iron and steel, hot enough to glow white hot, hot enough to vaporize most materials. But 3I Atlas, when the nickel was detected in late August, was about 3.5 AU from the Sun, more than 3 times farther than Earth. At that distance, temperatures are absolutely frigid, probably around negative 200 degrees Celsius to negative 150 degrees Celsius, negative 328 degrees Fahrenheit to negative 238 degrees Fahrenheit. depending on the exact distance and whether you're talking about sunlit surface or shadowed regions. At such temperatures, nickel should be frozen solid, locked into the comet's rocky components, as inert as the stones in a frozen field. So how is there nickel vapor around a comet at such cold temperatures? The research team was puzzled, but certain of their detection. It was pretty clear that it was nickel, Dr. Pouzier told reporters. The spectral lines matched nickel's fingerprint exactly, so it was super exciting. But exciting also meant mysterious, because there was no obvious explanation. Scientists proposed several theories to explain this bizarre observation. Theory 1. Cosmic ray processing. For billions of years while wandering through interstellar space, 3I Atlas was continuously bombarded by galactic, cosmic rays, high-energy particles, mostly protons, flying through the galaxy at near light speeds. When these cosmic rays slam into the comet's surface, they deposit enormous amounts of energy in tiny volumes. This energy breaks chemical bonds, creates exotic molecules, fundamentally alters the structure of ice and rock. Over billions of years, cosmic ray bombardment creates what scientists call an irradiated crust on the comet's surface, a layer centimeters or meters thick, where the material has been transformed by radiation. Some scientists hypothesize that this irradiated crust might contain nickel in some unusual chemical form that can release vapor at much lower temperatures than pure metallic nickel. Perhaps the nickel is in some exotic compound created by radiation damage. Perhaps the radiation created tiny pockets or structures that allow nickel to sublime at lower temperatures. Theory 2. Micrometeorite impacts. Even in interstellar space, 3I Atlas wasn't completely alone. Interstellar dust particles, microscopic grains drifting through space would occasionally collide with the comet. At the velocities involved, tens of kilometers per second, relative velocity, even tiny impacts generate significant heat in a very localized area, like a microscopic blowtorch hitting the surface. Maybe these micro-impacts vaporize nickel-rich minerals in the comet's surface material, creating transient puffs of nickel vapor. It wouldn't take much, just enough tiny impacts to produce a detectable signal when averaged over the entire visible surface of the comet. Theory 3. Subsurface heating. Perhaps there's some internal heat source not fully understood. Maybe radioactive decay of long-lived isotopes deep inside the comet generates heat. Maybe tidal forces from the sun's gravity, though at 3.5 AU, these would be very weak, create small amounts of internal friction and heating. Maybe something about the comet's internal structure, perhaps large void, spaces where sublimating ice accumulates pressure before bursting out, allows localized heating sufficient to vaporize metals. Theory 4. Catalytic reactions. Some researchers suggested that chemical reactions on the comet's surface, perhaps catalyzed by solar ultraviolet light or by the unusual chemistry of the irradiated crust, might produce nickel-containing compounds volatile enough to exist as vapor at low temperatures. The truth is, as of late 2025, scientists don't have a definitive answer. The nickel detection is real, multiple independent observations from different telescopes confirmed it. The spectral lines match nickel's fingerprint perfectly. But the mechanism that produces nickel vapor at temperatures far below nickel's normal vaporization point remains one of 3I Atlas's great mysteries, one that may require new understanding of how materials behave under exotic conditions. The comet continued revealing surprises as August progressed. On July 20th, 2025, near-infrared spectroscopic observations made by the Gemini South Telescope in Chile and NASA's Infrared Telescope facility in Hawaii definitively detected water ice in 3I Atlas's coma. The detection came from identifying characteristic absorption features of water ice in the near-infrared part of the spectrum, specific wavelengths where water molecules absorb light. By mid-August, NASA's Neil Gehrels Swift Observatory, a space telescope designed primarily to study gamma-ray bursts and other high-energy phenomena, but also capable of ultraviolet observations, detected hydroxyl OH radicals around 3I Atlas. Hydroxyl is actually a breakdown product of water. When water molecules, H2O, get hit by ultraviolet light from the sun, they can be photodissociated, breaking apart into OH and H. The presence of OH is indirect evidence of water vapor being produced as the comet heats up and water ice sublimates. Scientists measured the water production rate and found that by mid-August 2025, 3I Atlas was losing about 150 kilograms, 330 pounds, of water per second. That might sound like a lot. 150 kilograms per second is over 12 million kilograms per day, or about 13,000 tons per day. But for a comet estimated to be several kilometers across with a total mass of tens of billions of tons, this production rate is actually relatively modest. Some comets in our solar system, when they get very close to the Sun, inside 1 AU, can lose thousands of kilograms of water per second. The relatively low water production, combined with the high CO2 content, reinforced the conclusion that 3I Atlas formed in an unusually cold region where CO2 was more abundant than water, or at least where conditions favoured retention of CO2 over H2O. On August 22, 2025, astronomers at Lowell Observatory in Arizona tentatively detected hydrogen cyanide, HCN, in 3I Atlas's spectrum. The detection was confirmed by the Very Large Telescope on the same day. The James Clerk Maxwell Telescope, JCMT, in Hawaii, a 15-meter radio telescope specialized for submillimeter observations, measured the HCN production rate and found it was producing about 5 times 10 to the power of 25 molecules per second in early September, rising to about 5 times 10 to the power of 25 molecules per second by mid-September as the comet warmed up. Now, when most people hear cyanide, they think of poison, and yes, hydrogen cyanide is extremely toxic to humans, but in comets, HCN is actually perfectly normal and expected. Comets are ancient objects preserving the chemistry of the early solar nebula, or in this case, the nebula of whatever star system 3I Atlas came from. In the cold outer regions of protoplanetary disks, simple molecules like methane, CH4, ammonia, NH3, and water, H2O, undergo chemical reactions driven by ultraviolet light and cosmic rays. These reactions produce more complex molecules, including hydrogen cyanide. The presence of HCN tells scientists that 3I Atlas's parent system had the right conditions for basic organic chemistry. Carbon, nitrogen, and hydrogen, 3 of the essential elements for life as we know it, were present and reacting together to form simple organic molecules. This doesn't mean life existed in that system, but it does mean the basic chemical building blocks that could eventually lead to life were present. The reddish colour of 3I Atlas observed in July and August came from those organic compounds mentioned earlier, tholins. Carl Sagan coined the term tholins in the 1,970 seconds to describe complex organic molecules formed by irradiation of simpler compounds. They're not a single substance, but a class of materials, dark, reddish-brown organic polymers with complex carbon chains. Tholins form when simple molecules like methane, ethane, nitrogen, and others are exposed to ultraviolet light or energetic particles for extended periods. The radiation breaks bonds in simple molecules, creating highly reactive molecular fragments called free radicals. These radicals recombine in various ways, building increasingly complex organic molecules with long carbon chains, aromatic rings, and complex three-dimensional structures. The result is a reddish-brown tarry substance coating surfaces exposed to space for long periods. Tholins are found throughout the outer solar system. Pluto's surface is covered with them, giving it a reddish-brown hue. Neptune's moon, Triton, has them. Saturn's moon, Titan, has a whole atmosphere full of tholin haze, creating its characteristic orange appearance. The fact that 3I Atlas appeared reddish told scientists it had been in space for a very, very long time. Tholins don't form quickly. They need millions or billions of years of radiation exposure to build up significant layers. This ancient comet wore its history on its surface, the reddish colour, a badge of eons spent wandering through the galaxy. Recent observations with the James Webb Space Telescope suggested that 3I Atlas has an exceptionally thick irradiated crust, much thicker than typical comets in our solar system. Computer models of cosmic ray bombardment suggest that after 1 billion years of galactic cosmic ray exposure, the surface layers of a comet would be fundamentally transformed. The ice structure would be altered from crystalline to amorphous. Complex organic molecules would accumulate. The composition would no longer resemble the pristine materials from which the comet originally formed. In a real sense, 3I Atlas at discovery was wearing billions of years of history. It was like an ancient ship that had been sailing so long its hull was covered in barnacles, weathered by countless storms, transformed by its journey until it barely resembled the vessel that first set sail. As September arrived and 3I Atlas crossed the 2 AU mark about 300 million kilometers from the Sun, activity increased dramatically. Multiple observatories reported brightening the comet's magnitude increased from 17.5 at discovery in early July to around 15 by mid-September. It was becoming noticeably brighter. As more ice sublimated, more dust was released, and the coma expanded. Amateur astronomers with 8 to 12-inch telescopes and good cameras could now photograph 3I Atlas. The images showed a definite fuzzy appearance, clearly not a star-like point of light, but an extended object with a visible coma. Some images captured hints of a tail, though it remained faint and required careful image processing to detect. Professional observatories continued intensive monitoring. The goal was to characterize how the comet changed as it approached perihelion, building a complete picture of its evolution from dormant frozen relic to active comet. Then came October, and with it, 2 critical events that would define 3I Atlas's story: the close approach to Mars and perihelion itself. October 3rd, 2025, 4 UTC, midnight Eastern Time, on October 2nd. 3I Atlas makes its closest approach to Mars, passing just 29 million kilometers, 18 million miles, from the red planet. In everyday terms, 29 million kilometers is still quite far, about 75 times the distance from Earth to the Moon, or roughly 20% of the distance from Earth to the Sunday. But in cosmic terms, especially for an interstellar object, this is remarkably close enough for spacecraft orbiting Mars to observe the comet from a unique perspective. The European Space Agency had been preparing for this moment for months. They operate 2 spacecraft currently orbiting Mars: the ExoMars Trace Gas Orbiter, which arrived at Mars in 2016 and is designed to study the Martian atmosphere, and Mars Express, which has been orbiting Mars since 2003. Both spacecraft carry cameras and other instruments that can observe celestial objects. Think about how special this opportunity was. From Earth, astronomers see 3I Atlas from one specific viewing angle, with the Sun illuminating it in a particular way determined by the geometry of Earth's orbit. But from Mars, the viewing geometry is completely different. Mars orbits 1.5 AU from the Sun, compared to Earth's 1 AU. And at this particular moment, Mars happened to be positioned such that spacecraft there could see parts of the comet lit differently than from Earth's perspective. The spacecraft could potentially see portions of the nucleus that were in shadow from Earth's viewpoint. They could measure how the comet's brightness changed with viewing angle, which provides information about the shape and texture of the coma, about whether jets emanate from specific regions, about how dust particles scatter light at different angles. The ExoMars TGO trained its color and stereo surface imaging system camera on 3I Atlas during the close approach. This high-resolution camera, designed to photograph Mars's surface in detail, turned toward deep space to capture images of the interstellar visitor. The images showed the comet's coma and tail structure from Mars's unique vantage point. NASA's Mars Reconnaissance Orbiter, MRO, which has been orbiting Mars since 2006, also had the opportunity to observe the comet with its high-rise, high-resolution imaging science experiment camera, potentially the most powerful camera ever sent to another planet, capable of resolving features as small as about 30 centimeters across on Mars's surface. When pointed at 3I Atlas, 29 million kilometers away, HiRISE couldn't resolve the nucleus itself, which is only a few kilometers across, but it could capture the highest resolution images of an interstellar object's coma ever obtained. There's been some controversy about these MRO images. Harvard astronomer Avi Loeb stated publicly that NASA obtained remarkable images on October 2nd showing 3I Atlas when it was just 30 million kilometers from Mars, capturing details never before seen of an interstellar object. However, these images were never officially released to the public or to the broader scientific community. NASA hasn't formally commented on why the images weren't released, though several factors may have contributed. In early October 2025, the US government experienced a shutdown that disrupted normal operations at many federal agencies, including NASA. During government shutdowns, only essential personnel work, and routine data releases are often delayed or suspended. It's possible the MRO observations of 3I Atlas simply got caught in administrative delays. Alternatively, the images might be undergoing careful analysis before release. Scientific data from spacecraft often undergo weeks or months of calibration, processing, and validation before being made public. The images might eventually appear in peer-reviewed scientific papers without separate press releases, or, as some observers noted, the images might simply not have shown anything dramatically different from what ground-based and other space-based telescopes already observed, making them scientifically valuable but not warranting special public attention. Regardless of the Mars observation's status, the close approach itself was scientifically valuable simply for providing that different viewing angle. Data from spacecraft at Mars, combined with simultaneous observations from Earth, allowed triangulation using geometry to better constrain the comet's position, trajectory, and physical properties. As October progressed into its third week, 3I Atlas approached solar conjunction. This is a critical concept in observational astronomy that anyone studying objects in the inner solar system must understand. Solar conjunction occurs when an object appears close to the Sun in Earth's sky. From our perspective, the object is in approximately the same direction as the Sun, not physically close to the Sun necessarily, but appearing close from our viewing angle. During conjunction, the object becomes impossible to observe from ground-based telescopes because looking in that direction means looking essentially toward the Sunday. This isn't just difficult, it's impossible with normal telescopes. The Sun is so overwhelmingly bright that even when an object is several degrees away from the Sun's disk, the scattered sunlight in Earth's atmosphere creates a bright blue sky that drowns out everything else. That's why stars can't be seen during the day, except the Sun itself. They're still there, still shining, but the scattered sunlight overwhelms them. Pointing a telescope directly at or near the Sun is also dangerous. Solar radiation, concentrated by telescope optics, can destroy sensitive detectors, melt components, and if someone were looking through an eyepiece, cause immediate permanent eye damage or blindness. Professional observatories have strict safety protocols preventing telescopes from being pointed anywhere near the Sunday. 3I Atlas entered solar conjunction around October 21st, 2025, about a week before perihelion. From Earth's perspective, the comet moved into the Sun's glare and effectively vanished from view for ground-based observers. Amateur astronomers who had been photographing it nightly could no longer see it. Professional observatories lost their ability to track it. But solar conjunction didn't mean 3I Atlas disappeared from all observations. Several space-based solar observatories, satellites specifically designed to watch the Sun and the space environment around it, could still detect the comet. NASA's Stereo A, Solar Terrestrial Relations Observatory A, spacecraft, has been orbiting the Sun since its launch in 2006. Stereo was originally part of a two-spacecraft mission, Stereo A and Stereo B, designed to provide stereoscopic views of the Sun, watching solar activity from multiple angles. Stereo B lost contact with Earth in 2014, but Stereo A continues operating. Stereo A carries a suite of instruments called SECI-SUN, Earth Connection, Coronal and Heliospheric Investigation, that includes several telescopes and cameras designed to observe the Sun's corona and the space around. The Sunday, because Stereo A orbits the Sun rather than Earth, its viewing geometry is different from Earth's. When 3I Atlas was in conjunction, as seen from Earth, it wasn't necessarily in conjunction as seen from Stereo A's position. The SOHO spacecraft, Solar and Heliospheric Observatory, a joint NASA-ESA mission that's been observing the Sun since 1995, sits at the L1 Lagrange point between Earth and the Sun, about 1.5 million kilometers from Earth. SOHO carries instruments called coronagraphs that are specifically designed to observe the sun's faint corona by blocking out the sun's bright disk with an occulting disk, essentially an artificial eclipse created inside the instrument. These coronagraphs can detect objects passing through their field of view near the Sunday. In fact, SOHO has discovered over 4,000 comets, mostly small sun-grazing comets, that pass extremely close to the Sunday. These discoveries happen accidentally while the coronagraphs are watching for coronal mass ejections and other solar phenomena. NOAA's GOES-19 weather satellite, launched in 2024 as part of the Geostationary Operational Environmental Satellite Program, carries an instrument called the Compact Coronagraph, CCOR-1, designed to observe the sun's corona for space weather monitoring. Like SOHO's coronagraphs, CCOR-1 can detect objects passing near the sun in its field of view. Amateur comet hunter Wachate Boonplod, who regularly monitors publicly available images from solar observatories looking for comets, spotted 3I Atlas in GOES-19 coronagraph data during its conjunction passage. This discovery by an amateur astronomer monitoring professional satellite data exemplifies how modern astronomy combines professional facilities, space-based assets, and dedicated amateur contributions. These space-based observations during conjunction turned out to be absolutely crucial because they revealed something unexpected about what happened to 3I Atlas at perihelion. October 29, 2025, approximately 14 UTC, 3I Atlas reaches perihelion, its closest approach to the Sunday. At this moment, the comet sits at a distance of 1.36 astronomical units from the Sun, equivalent to about 203 million kilometers or 126 million miles. To put this in perspective, that's farther from the Sun than Earth, which orbits at 1 AU by definition, but closer than Mars, which orbits at about 1.5 AU. If someone could somehow stand on 3I Atlas at perihelion, the Sun would appear about 26% smaller in angular diameter than it appears from Earth, but it would still be intensely bright, the overwhelming dominant feature in the sky. At this distance, the solar radiation hitting the comet's surface amounts to approximately 735 watts per square meter. For reference, Earth receives about 1,361 watts per square meter at its average distance. So 3I Atlas at perihelion receives roughly 54% of the solar energy flux that Earth receives, about half. This might not sound like much, but remember that for billions of years, this comet received essentially 0 watts per square meter while wandering through interstellar space at temperatures just a few degrees above absolute zero. For a nucleus estimated to be roughly 5 kilometers in diameter, though this estimate has substantial uncertainty, ranging from perhaps 3 to 8 kilometers depending on how reflective the surface is, the total solar energy hitting the comet at perihelion amounts to at least 33 gigawatts, 33 billion watts. That's roughly equivalent to the power output of about 30 large nuclear power plants, all focused on an object roughly the size of Manhattan Island. What happens when you take something that's been frozen at near absolute zero temperatures for billions of years and suddenly expose it to 33 gigawatts of solar radiation? First, surface ices begin sublimating explosively. Carbon dioxide ice, water ice, carbon monoxide ice, all turn directly from solid to gas without passing through a liquid phase, sublimation. The gas expands rapidly, accelerating to speeds of hundreds of meters per second as it flows away from the nucleus. This isn't gentle evaporation like water slowly evaporating from a puddle. It's vigorous, violent outgassing. Second, this outflowing gas carries dust particles with it. Dust that was frozen into the ice matrix, tiny grains of rock, carbon, and organic materials, is released as the ice around it vaporizes. The gas drag entrains dust particles and carries them away from the nucleus, creating the visible coma and tail. Third, as surface ice sublimates away, it exposes fresh ice beneath to sunlight. This fresh ice then begins sublimating, which exposes more fresh ice below it, creating a self-sustaining cycle. The sublimation zone migrates into the comet's interior, releasing material that has been frozen and preserved since the comet's formation. Fourth, and this is important for temperature considerations, sublimation itself cools the surface through evaporative cooling. This is the same physics that makes sweat feel cold on skin or makes evaporating rubbing alcohol feel cold. When a liquid, or ice, evaporates or sublimates, it absorbs heat from its surroundings, lowering the local temperature. 2.2. Sublimating from 3I Atlas's surface absorbs heat energy, actually cooling the surface even as the sun beats down on it. This evaporative cooling creates a balance. Solar heating drives sublimation, but sublimation cools the surface, preventing it from getting as hot as a process non-volatile surface would get at the same distance. The surface temperature reaches an equilibrium determined by the balance between solar heating and evaporative cooling. At 1.36 AU, the equilibrium temperature for a dark, non-volatile surface, like rock or carbon, would be around 200 to 250 Kelvin, negative 73 degrees Celsius to negative 23 degrees Celsius, or negative 100 degrees Fahrenheit to negative 10 degrees Fahrenheit. But 3I Atlas's surface, actively sublimating CO2 and water, probably stays colder, perhaps 180 to 220 Kelvin, negative 93 degrees Celsius, to negative 53 degrees Celsius, or negative 136 degrees Fahrenheit to negative 64 degrees Fahrenheit, depending on the sublimation rate and the balance of different ices. Still cold by human standards, but incomprehensibly warmer than the 2 to 10 Kelvin, negative 271 degrees Celsius to negative 263 degrees Celsius, or negative 456 degrees Fahrenheit to negative 442 degrees Fahrenheit, the comet experienced during billions of years in interstellar space. At perihelion, hidden from Earth's view behind the sun's glare, something dramatic happened to 3I Atlas. Researchers Qicheng Zhang, an independent astronomer specializing in comets and asteroids, and Carl Batham's astronomer at the Naval Research Laboratory and lead for NASA's Sun-Grazing Comets project, were monitoring data from multiple space-based solar observatories, Stereo A's Secchi instrument, SOHO's LASCO coronagraph, and GOES 19's CCOR-1 coronagraph. What they discovered, analysing images captured between mid-September and late October, was astonishing. Between approximately September 15th, when 3I Atlas was around 2 AU from the Sun, and October 29th perihelion, at 1.36 AU, the comet brightened dramatically, far faster than comets typically brighten as they approach the Sunday. Normal cometary brightening follows a predictable pattern based on the inverse square law of light. The closer you get to the Sun, the more light the comet reflects, and the more light we receive from it. But 3I Atlas brightened approximately twice as fast as this standard model predicted. By perihelion, it had reached apparent magnitude 9 bright enough to be easily visible through amateur telescopes if only it weren't hidden in the sun's glare. Zhang and Batams published their findings in an astronomer's telegram, a rapid communication bulletin for time-sensitive astronomical discoveries, noting the unusual brightness surge. They calculated that the actual intrinsic brightness of the comet, how much light it was producing, not just how bright it appeared, had increased by a factor of roughly 4 to 6 compared to predictions based on early observations. This suggested either that the comet's activity had surged dramatically, releasing much more dust and gas than anticipated, or that something about its surface properties had changed, making it reflect light more efficiently, or both. But brightness wasn't the only surprise. The colour changed. Earlier observations in July through September showed 3I Atlas appearing reddish, with colours similar to many outer solar system objects. The reddish tint made sense. Tholins coating the surface are reddish-brown, and dust particles tend to scatter red light more efficiently than blue light. This is why sunsets are red. Shorter wavelength blue light scatters in all directions, while longer wavelength red light passes through more directly. But space-based observations during perihelion, particularly from Stereo A and GOES 19, revealed that 3I Atlas had turned blue, not just slightly blue, but distinctly bluer than the Sun, according to the technical analysis by Zhang and Batams. This is profoundly weird for several reasons. First, dust should redden light, not blue it. When sunlight scatters off dust particles, the scattering preferentially affects shorter wavelengths, blue light, more than longer wavelengths, red light. This is called Rayleigh scattering, when particles are smaller than the wavelength of light, or Mie scattering, when particles are comparable to or larger than the wavelength. Either way, the net effect is that scattered light appears redder than the incident light. A dusty comet should look reddish. Second, temperature physics suggests red, not blue. Objects emit thermal radiation according to their temperature, following Planck's blackbody radiation law. The sun's surface, the photosphere, is about 5,800 Kelvin, which makes it appear yellowish-white. An object cooler than the sun emits light that peaks at longer, redder wavelengths. Second, temperature physics suggests red, not blue. Objects emit thermal radiation according to their temperature, following Planck's blackbody radiation law. The sun's surface, the photosphere, is about 5,800 Kelvin, which makes it appear yellowish-white. An object cooler than the sun emits light that peaks at longer, redder wavelengths. At 1.36 AU, even the sunlit side of 3I Atlas's nucleus probably only reaches 180 to 250 Kelvin at most, far colder than the Sunday. By thermal emission physics, 3I Atlas should appear much redder than the sun, not bluer. Third, the surface tholins are reddish-brown. Those organic compounds formed by billions of years of cosmic ray bombardment are known to be red. They're what makes Pluto reddish, what gives Titan its orange haze. They should contribute red coloration, not blue. Yet 3I Atlas was glowing blue at perihelion, distinctly, measurably bluer than the Sunday. The leading explanation proposed by most planetary scientists involves ionized gas emission rather than reflected or scattered sunlight. Here's the hypothesis. At perihelion, CO2 ice sublimates vigorously, releasing enormous quantities of CO2 gas into the coma. Solar ultraviolet radiation, particularly the intense UV at wavelengths shorter than about 200 nanometers, can break CO2 molecules apart through a process called photodissociation. CO2 plus UV photon, CO plus O. The carbon monoxide CO produced by this breakdown can then be ionized by solar radiation, losing an electron and becoming CO minus, ionized carbon monoxide. CO plus UV photon CO minus plus electron CO minus ions are in excited energy. States electrons occupy higher energy orbitals than they would in a ground state. These excited ions eventually relax back to lower energy states, and when they do, they emit photons at specific wavelengths determined by the quantum mechanical energy level structure of the CO minus ion. It happens that CO minus has strong emission bands in the blue and violet parts of the visible spectrum, particularly around 420 nanometers, violet blue, and throughout the 400 to 500 nanometer range. If 3I Atlas was producing massive amounts of CO minus at perihelion, which makes perfect sense given its high CO2 content and the intense solar UV at 1.36 AU, then the blue emission from CO minus could overwhelm the reddish, scattered sunlight from dust, creating that distinctive blue glow. This explanation has the advantage of being physically plausible, matching known chemistry, and explaining the blue color as a direct consequence of 3I Atlas's unusual composition, high CO2 encountering intense solar radiation at perihelion. Most planetary scientists consider this the likely explanation. The blue color is a chemical signature, a fingerprint revealing 3I Atlas's exotic CO2-rich composition and how it responds to perihelion heating. However, Harvard astronomer Avi Loeb, who has been following 3I Atlas closely since discovery, posed a provocative question in public statements and on social media. The appearance of 3I Atlas as bluer than the sun is very surprising. Does it employ a power source that is hotter than the sun? Loeb's question raises an intriguing alternative. What if the blue color isn't just CO minus emission? What if there's some internal heat source, some process generating temperatures higher than expected for simple solar heating? Could there be exothermic chemical reactions occurring? Could there be heat from radioactive decay concentrated in unusual ways? Could there be, and here, Loeb edges toward his signature, speculation, some artificial heat source? Most scientists consider these alternative explanations unnecessary. The CO-MICE emission hypothesis explains the observation without requiring exotic physics or unprecedented processes. Occam's razor, the principle that simpler explanations should be preferred when they adequately explain the data, favours the straightforward chemical explanation. But Loeb's question isn't scientifically invalid. Science progresses by considering multiple hypotheses and testing them against observations. The December 2025 observations should provide more data to distinguish between these possibilities. If the blue colour fades as the comet recedes from the Sun and CO2 production decreases, that would strongly support the CO-MICE emission explanation. If the blue colour persists despite decreasing activity, that would be puzzling and might require reconsidering alternatives. If spectroscopy directly detects strong CO-MICE emission lines at blue wavelengths, that would essentially prove the CO-MICE hypothesis. But there was another mystery revealed by observations around perihelion: non-gravitational acceleration. When scientists track the position of asteroids and comets over time, they use Newton's laws of gravity, or Einstein's general relativity for extra precision, to predict where the object should be at any given future time. If you know an object's position, velocity, and the gravitational forces acting on it, you can calculate its entire future trajectory. For most asteroids, this works perfectly. Observations match predictions to within measurement uncertainty. The asteroid follows its gravitational orbit precisely, but comets often deviate slightly from purely gravitational trajectories. Their observed positions don't match predictions based on gravity alone. This is called non-gravitational acceleration, and it's been known since the 19th century, when astronomers noticed that comet Encke's orbit was gradually changing in ways that gravity couldn't explain. The usual explanation is the rocket effect, or outgassing force. When a comet gets warm enough, ice is sublimate from its surface. The gas expands rapidly and flows away from the nucleus at high speed, typically 300 to 800 meters per second, depending on the molecular weight of the gas and the temperature. This outflowing gas carries momentum. By Newton's third law, every action has an equal and opposite reaction. The gas flowing off the comet in one direction pushes the comet itself in the opposite direction, like a rocket engine. The magnitude of this thrust depends on how much gas is being released, the mass flow rate, and how fast it's flowing, the velocity. The direction of the thrust depends on where on the nucleus the gas is flowing from and how the nucleus is rotating. If gas flows primarily from the sunward side, the most strongly heated, the thrust pushes the comet away from the Sun, creating what's called radial acceleration. If the nucleus is rotating and has active regions, jets, on specific parts of its surface, the gas release can create sideways push, transverse acceleration. For 3I Atlas, signs of non-gravitational acceleration were first reported by Davide Farnocchia, a navigation engineer at NASA's Jet Propulsion Laboratory, who specializes in calculating precise orbits of comets and asteroids. Using observations spanning from discovery in July through October, Farnocchia and colleagues detected deviations from a purely gravitational trajectory. The measurements showed radial acceleration, approximately 135 kilometers per day squared, directed away from the Sun, transverse acceleration, approximately 60 km day squared, perpendicular to the Sun-comet line. These numbers require some translation to make sense. An acceleration of 135 kilometers day squared means the comet's velocity is changing by 135 kilometers per day every day in the radial direction. That sounds large, but remember, we're talking about changes accumulated over days and weeks. Let's convert to more familiar units. 135 km divided by day squared equals about 1.56 times 10 to the power of negative 6 meters per second squared. That's 0.000000156 meters per square second. For comparison, Earth's surface gravity is 9.8 meters per square second. The acceleration from cometary outgassing is roughly 1/6 millionth of Earth's gravity, absolutely tiny. But tiny doesn't mean undetectable or unimportant. When this small acceleration acts continuously over weeks, it adds up. After 1 month, 30 days of constant acceleration at 135 km day squared, The comet's position would deviate from the gravity-only prediction by roughly distance equals half times acceleration times time squared equals half times 1.56 times 10 to the power of negative 6 m divided by s squared times 30 days times 86,400 s divided by day squared approximately equal to 10,000 kilometers. 10,000 kilometers is easily measurable with modern telescopes and astrometric techniques. So even though the acceleration is tiny, its cumulative effect on the orbit is definitely detectable. The radial component, 135 kilometers, day squared outward, is consistent with standard cometary outgassing from the sunward hemisphere, pushing the comet away from the sunday. The transverse component, 60 km, day squared perpendicular, suggests asymmetric outgassing, perhaps jets more active on one side of the nucleus than the other, or rotation causing preferential gas release that creates sideways push. For many short-period comets in our solar system, non-gravitational accelerations of this magnitude are completely normal. Some comets show much larger accelerations, so in principle, there's nothing extraordinary about 3I Atlas experiencing this level of non-gravitational force. However, Avi Loeb performed a calculation that raised questions. Using conservation of momentum and the rocket equation, Loeb calculated how much mass 3I Atlas would need to eject to produce the observed acceleration. His analysis went like this. The momentum carried away by outgassing gas equals the mass of gas ejected, multiplied by its velocity. P, gas, equals m, gas times v gas. By momentum conservation, the comet experiences an equal and opposite momentum change. P, comet equals p gas. This momentum change over time creates acceleration. A, comet, is gelijk aan rate of momentum change, gedeeld door comet mass, is gelijk aan dms, gedeeld door d times v, gedeeld door m, comet rearranging. dm, gas divided by dt equals A comet times m, comet divided by v gas. Now plug in numbers. A comet approximately equal to 1.56 times 10 to the power of negative 6 minus squared, the observed acceleration. M, comet approximately equal to 3 times 10 to the power of 13 kg estimated from the comet's size and assumed of got density. V, gas approximately equal to 500 meters per second, typical for CO2 outgassing. This gives dm, gas, dt, approximately equal to 1.56 times 10 to the power of negative 6 times 3 times 10 to the power of 13, 500, approximately equal to 9 times 10 to the power of 4 kg s. That's about 90,000 kilograms per 5 second, or roughly 8 billion kilograms per day, 8 million metric tons per day. If this mass loss rate persisted for the approximately 30-day period around perihelion, when the first acceleration was most significant, total mass loss would be about 240 billion kilograms, or roughly 8% of the comet's estimated total mass. If the comet's mass estimate is lower, say 2 times 10 to the power of 13 kg, or if the acceleration persisted longer or was higher than measured, the percentage mass loss could be 10-13%, as Loeb stated in various interviews. Loeb's argument: when observers see 3I Atlas in December 2025 as it approaches Earth, there should be clear evidence of this massive mass loss. If the comet lost 8-13% of its mass at perihelion, that's billions of tons of material. Such enormous mass loss should create a massive, visible cloud, a huge coma and tail that would be obvious in observations. The gas production rates should be substantial and measurable with spectroscopy. He continued proportion to, if December observations show the expected level of gas and dust production, great, it confirms natural cometary outgassing. But if observations show much less activity than expected for such large mass loss, then we need another explanation for the acceleration. The controversy here isn't the non-gravitational acceleration itself that's well established from tracking the comet's position. The controversy is about interpretation. Most planetary scientists expect that December observations will show robust outgassing, confirming the natural explanation. They argue, 1. Comets can have dramatic outbursts at perihelion where activity spikes suddenly then decreases. The mass loss might have been concentrated in brief intense bursts rather than steady release, making it less visually dramatic than sustained release would be. 2. The outgassing doesn't have to be visible as one giant cloud. The gas and dust released weeks ago have spread out over millions of kilometers by now. They might not appear as a dramatic concentrated coma, but rather as a diffuse extended structure. 3. If gas composition is unusual, that high CO2 content visibility might differ from typical comets. CO2 gas is transparent, you can't see it directly, like you can't see the CO2 coming out of a soda bottle. You only detect it spectroscopically or by the dust it carries. If the dust-to-gas ratio is lower than normal comets, there might be substantial gas production but modest visible dust. 4. The comet's mass might be larger than estimated, meaning 813% represents more total mass than calculated. Size estimates are uncertain because they depend on assumptions about how reflective the surface is, the albedo, which is unknown. If the comet is darker than assumed, it's larger than estimated, meaning 813% is a larger absolute amount of mass. 5. The outgassing might be more efficient than typical, producing more thrust per unit mass than standard models predict. Perhaps the high CO2 content creates faster gas velocity. Perhaps the surface structure, porous versus compact, affects efficiency. These are all reasonable scientific explanations for why observations might not show a dramatically obvious mass loss cloud, even if substantial mass was ejected. The December 2025 observations will provide definitive answers. If strong gas emission lines appear in spectroscopy, if the coma is large and bright, if dust production is high, then the natural outgassing explanation is confirmed. If observations show modest activity, inconsistent with 813% mass loss, then scientists will need to refine their models or consider alternative explanations. Either outcome will be scientifically valuable. Either we confirm our understanding of cometary outgassing applies to interstellar visitors, or we learn something new about how these objects behave. But regardless of the resolution, the key lesson remains. Perihelion is where an object's true nature is revealed. The heating, the stress, the transformation, they strip away mystery and expose fundamental properties. To truly understand what happened to 3I Atlas at perihelion and what happens to Earth, Mercury, and every orbiting object at their closest approach requires understanding the physics that Kepler observed but couldn't explain. That understanding came from Isaac Newton. In 1687, Newton published his Philosophia Naturalis Principia Mathematica, Mathematical Principles of Natural Philosophy, usually called simply the Principia. In this monumental work, Newton introduced his law of universal gravitation and showed how it explains all three of Kepler's laws and much more. Newton's law of universal gravitation states, every particle of matter in the universe attracts every other particle, with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. Written as an equation, F equals G times m1 times m2 divided by r squared, where F is the gravitational force, measured in newtons. G is the gravitational constant, approximately 6.674 times 10 to the power of negative 11, m squared, kg squared. m1 and m2 are the masses of the two objects, measured in kilograms. R is the distance between their centers, measured in meters. This simple inverse square law explains everything about measure. Orbits. It explains why Kepler's first law works. Elliptical orbits emerge naturally when solving Newton's equations of motion for a point mass under an inverse square force. Depending on the object's total energy, the solution is an ellipse, negative total energy, bound orbit, parabola, exactly zero total energy, or hyperbola, positive total energy, like 3I Atlas. It explains Kepler's second law, equal areas in equal times. This law is actually just conservation of angular momentum in disguise, and angular momentum is automatically conserved for any central force like gravity, where the force always points toward a central object. It explains Kepler's third law, the t-square, is proportional to a cubed relationship. This falls out mathematically when you solve Newton's equations for circular or elliptical orbits and relate the period to the orbital radius. But most importantly, for understanding perihelion, Newton's gravity explains why objects speed up when they approach the sunday. The explanation involves energy, specifically the law of conservation of energy, which states that the total energy of an isolated system remains constant over time. Energy can change forms, but it can't be created or destroyed. For an object orbiting the Sun, there are two types of energy to consider: kinetic energy, energy from motion, given by Ke equals half mv squared, where m is the object's mass and v is its velocity. The faster an object moves, the more kinetic energy it has. Gravitational potential energy, energy from position in the Sun's gravitational field, given by Pe equals gm, Sun times m divided by r, where g is the gravitational constant, m, Sun is the Sun's mass, m is the object's mass, and r is the distance from the Sun's center. The negative sign is important. It indicates that gravitational potential energy is defined as zero at infinite distance and becomes more negative lower as you get closer to the sunday. The total energy is the sum. E total equals Ke plus Pe equals half mv squared. Gm, Sun times m divided by r. For a bound orbit like Earth's, total energy is negative, meaning the object doesn't have enough energy to escape to infinity. For an unbound trajectory, like 3I atlases, total energy is positive, meaning the object has more than enough energy to escape. Here's the crucial point. Total energy remains constant throughout the orbit. As the object moves, kinetic and potential energy change, but they change in complementary ways, such that the sum stays the same. Consider Earth moving from aphelion toward perihelion. At aphelion, 152.1 million km, Earth is relatively far from the Sun, so the gravitational potential energy is high, less negative, closer to zero. As Earth moves inward toward perihelion, the distance r decreases. Decreasing r makes the potential energy more negative, lower. To keep total energy constant, kinetic energy must increase to compensate. Increasing kinetic energy means increasing velocity. Earth speeds up. At perihelion, 147.1 million kilometers, Earth has fallen 5 million kilometers deeper into the Sun's gravitational well. That change in potential energy has been converted to kinetic energy. Earth is moving faster. Then, as Earth climbs back out toward aphelion, the process reverses. Distance r increases. Potential energy becomes less negative. Kinetic energy decreases to keep total energy constant. Earth slows down. The same physics applies to 3I Atlas, just with different numbers. When far from the Sun at 5 AU, large r means high, less negative potential energy, low kinetic energy moving slowly at 3035 km per second. Total energy is positive, unbound trajectory, as it falls toward perihelion at 1.36 AU. Decreasing r means decreasing more negative potential energy, kinetic energy. Increases dramatically, accelerating to 61 km per second. Total energy remains the same positive value after perihelion. Climbing back out. Increasing r means increasing potential energy. Kinetic energy decreases, slowing down. Total energy still stays constant. The beautiful thing about this explanation is its universality. The same principle applies to everything. Earth's gentle seasonal speed variation, Mercury's dramatic 50% speed change between perihelion and aphelion, 3I Atlas's acceleration from 30 km per second to 61 km per second, spacecraft using gravity assists to reach outer planets, even binary stars orbiting each other. Conservation of energy is one of the most fundamental principles in all of physics. It's not just a convenient mathematical trick, it's a deep statement about the structure of reality. The German mathematician Emmy Noether proved in 1915 that conservation laws arise from symmetries in nature. Energy conservation comes from time translation. Symmetry, the fact that the laws of physics don't change over time. There's another conservation law crucial for understanding perihelion: conservation of angular momentum. Angular momentum measures rotational motion. For an object orbiting the Sun, Angular momentum depends on three things: the object's mass, m, its distance from the Sun, m, its velocity perpendicular to the radius. The formula is L equals m times r times v, perp. Here's the key insight. Angular momentum is conserved for any object moving under a central force like gravity, as long as no external torques act on the system. This means m times r times v, perp equals constant throughout the orbit. Watch what this tells us. At perihelion, small r, close to Sun, to keep L constant, v perp must be large, the object moves fast. At aphelion, large r, far from Sun, to keep L constant, v perp must be small, the object moves slowly. This is Kepler's second law, the law of equal areas in equal areas, times expressed in the language of physics. The equal areas law and conservation of angular momentum are actually the same thing, just stated differently. For Earth, at perihelion, proportion to L equals m times 147.1 million kilometers times 30.29 kilometers per second. At aphelion, proportion to L equals m times 152.1 million kilometers times 29.29 kilometers per second. Both expressions equal approximately 4,454 million klasers squared, so the mass cancels out. Angular momentum is conserved just as the physics predicts. For 3I Atlas, the same principle applies. As it fell from 5 AU to 1.36 AU perihelion, its distance decreased by a factor of 3.7. Conservation of angular momentum requires that its perpendicular velocity increased proportionally, accounting for the fact that not all velocity is perpendicular at all points in the orbit. Both conservation laws, energy and angular momentum, work together to completely determine orbital motion. Given an object's position and velocity at any one moment, these conservation laws plus Newton's gravity allow calculation of the entire future and past trajectory. This is why astronomers can predict where planets will be centuries in advance, why spacecraft trajectories can be calculated years before launch, why we knew exactly when comet Neowise would appear in 2020, or when comet Tsuchinshan Atlas would grace our skies in 2024. The universe follows rules, precise, mathematical, beautiful rules. November 15th, 2025. 3I Atlas has emerged from behind the Sunday. After 2 weeks hidden in solar glare during conjunction, the comet is visible again from Earth, moving through the constellation Virgo in the pre-dawn sky, heading outward on its journey back to interstellar space. Professional observatories worldwide have resumed intensive monitoring. The Hubble Space Telescope has multiple observation sessions scheduled. The James Webb Space Telescope is preparing follow-up near-infrared spectroscopy to compare with the August, pre-perihelion data. Ground-based telescopes from Chile to Hawaii are measuring brightness, tracking changes in the coma, analysing composition through spectroscopy. Amateur astronomers with 10-inch or larger telescopes and sensitive CCD cameras are photographing the comet nightly, contributing valuable brightness measurements and timing data to complement professional observations. Networks of small robotic telescopes scan the comet continuously, watching for any sudden changes or outbursts. The critical moment approaches, December 19th, 2025, when 3I Atlas makes its closest approach to Earth at 1.8 AU, approximately 270 million kilometers, or 167 million miles. That distance is still vast, about 700 times the Earth-Moon distance, comparable to the distance from the Sun to Mars at Mars's average orbital distance. But it's the optimal moment for detailed Earth-based observations because the comet will be well positioned in the night sky, away from the Sun's overwhelming glare, and at its minimum distance from our telescopes and instruments. The International Asteroid Warning Network, IAWN, has coordinated an ambitious observing campaign running from late November through late January 2026. The campaign involves dozens of professional observatories and hundreds of amateur astronomers worldwide. The goal is comprehensive characterization of 3I Atlas's post-perihelion state, answering the questions raised by the perihelion passage. What exactly are astronomers looking for? Several specific observations will address the key mysteries. 1. Gas production rates. Spectroscopy can detect emission lines from molecules like H2, OCO, 2CO, HCN, NH3, CH4, and others. By measuring the strength intensity of these emission lines, scientists calculate how many molecules per second the comet is producing. 2. Coma size and structure. High-resolution imaging reveals the coma's size, shape, and internal structure. A. Large, bright coma with clear jets or shells indicates robust ongoing activity. 3. Dust properties. By analysing how the coma scatters sunlight at different wavelengths and measuring polarization, scientists determine the size distribution of dust particles and their composition. 4. Nuclear size estimate. While the nucleus itself is too small to resolve directly, careful analysis of total brightness and coma properties can constrain the nucleus size more precisely than current estimates. 5. Rotation period. If the nucleus is irregular in shape, its brightness should vary periodically as it rotates. Monitoring brightness over hours and days can reveal this rotation period. 6. Fragmentation evidence. Did the intense heating and thermal stress at perihelion cause the nucleus to crack or break apart? 7. Color evolution. Is the comet still blue, or has it returned to its earlier reddish appearance? 8. Non-gravitational acceleration tracking. Is the comet still experiencing acceleration from outgassing, or has it returned to a purely gravitational trajectory? The observations continue through December and into January 2026. Data flows in from telescopes spanning the globe. Preliminary results appear on social media, in astronomers' telegrams, and in preprints. By February 2026, the picture becomes clear. The comprehensive dataset from this unprecedented observation campaign provides definitive answers about 3I Atlas's nature, confirming or refuting the various hypotheses about its composition, activity, and the mysterious phenomena observed at perihelion. Mid-November 2025, as this video is produced. 3I Atlas continues its outward journey, currently about 1.8 to 2 AU from the Sun, travelling at approximately 50 km per second through space. It appears as a faint, fuzzy object in the pre-dawn sky for observers equipped with appropriate telescopes. Professional observatories photograph it nightly, building datasets for scientific analysis. Amateur astronomers contribute brightness measurements and timing data. Space telescopes prepare for December's critical observations around closest approach to Earth. December will bring answers to the questions raised by perihelion. January will bring detailed analysis. By early 2026, scientists will know whether 3I Atlas is a natural comet with unusual but explainable chemistry, or whether its mysteries run deeper. But regardless of December's revelations, 3I Atlas has already taught profound lessons. It demonstrated perihelion's transformative power. An object frozen for billions of years awakened violently when exposed to solar heating, revealing hidden properties through explosive outgassing, dramatic brightening, and mysterious color changes. It showed that the same physical laws govern everything. Earth's gentle seasonal variations, Mercury's extreme temperature swings, and an interstellar comet's explosive awakening all follow. Identical principles: conservation of energy, conservation of angular momentum, Newton's gravity, and Kepler's geometric relationships. It illustrated how modern astronomy combines multiple capabilities: space telescopes, ground-based observatories, spacecraft at Mars, solar monitoring satellites, and amateur observers worldwide, working in coordination, built the comprehensive dataset needed to study this fleeting visitor. It revealed gaps in understanding: the nickel vapor at impossible temperatures, the blue color requiring explanation, the precise balance between outgassing and acceleration. These mysteries will drive future research and potentially reveal new physics of cometary behavior. It connected humanity to the larger galaxy. 3I Atlas reminded observers that our solar system exists within a galaxy where material constantly moves between stellar systems, where wanderers from distant stars occasionally pass through our neighborhood, where perihelion passages reveal what these visitors are and where they came from. In a few years, 3I Atlas will cross beyond Neptune's orbit at 30 AU, fading beyond the reach of all but the largest telescopes. In a decade, It will be 100 AU distant, in the region where the sun's gravitational influence begins to fade and the galactic environment dominates. In a century, it will be thousands of AU away, truly interstellar again. Perhaps in millions or billions of years, it will encounter another star system, and astronomers there will detect it, study it, and wonder about its origins. Perhaps they'll notice signatures of 21st century human technology, radar reflections, laser altimetry marks, or spectral signatures of spacecraft instruments, and realize this wanderer once passed through a system where curious beings observed it. Or perhaps 3I Atlas will drift forever through the galaxy's dark spaces, never again approaching a star. Its encounter with our sun, a unique moment in billions of years of wandering. Meanwhile, on January 4th, 2026, Earth will reach its own perihelion, completing another annual cycle. The planet will be moving at 30.29 kilometers per second, receiving 7% more solar energy than at aphelion, following the same elliptical path it has traced for 4.5 billion years. Most people won't notice. Winter will continue in the northern hemisphere despite Earth's closest solar approach. The seasons will follow their axial tilt-dominated pattern. But after watching this video, understanding perihelion's physics and significance, viewers see winter differently. Earth is at perihelion, moving fastest, zipping through this portion of its orbit in the yearly dance around the Sunday. The same laws that govern Earth's motion governed 3I Atlas's explosive perihelion passage. The same conservation principles, the same gravitational forces, the same elegant mathematics discovered by Kepler and explained by Newton. This is perihelion, that point of closest approach, where speed maximizes, where heating peaks, where transformation occurs, where truth emerges. That moment where potential energy converts to kinetic, where distance determines velocity, where the abstract mathematics of orbital mechanics becomes physical reality. That elegant point where conservation laws, geometric relationships, and physical forces align to create observable phenomena accessible to human understanding. The cosmos continues its dance. Planets orbit stars. Comets sweep through inner solar systems. Interstellar visitors pass through from distant origins, all governed by perihelion, that fundamental concept encoding how objects move under gravity's influence. The next interstellar visitor approaches even now, years away from detection, following its own trajectory toward its own perihelion passage through our solar system. When it arrives, telescopes will track it, spectrographs will analyze it, and through perihelion, its secrets will be revealed. Humanity will watch, measure, and understand, continuing the ancient quest to comprehend the cosmos through observation, mathematics, and reason. The universe follows rules, beautiful rules, precise rules, knowable rules, and perihelion is where those rules reveal themselves most clearly. If you've made it this far through this video, thank you. Seriously. This has been an in-depth journey through one of astronomy's most elegant concepts, spanning everything from Kepler's centuries of hand calculations to an interstellar comet's mysterious transformation happening right now in our skies. 3I Atlas is still out there as you watch this, moving through space at tens of thousands of miles per hour, carrying secrets from another star system, possibly revealing those secrets through the December observations happening at this very moment. Within weeks, scientists will have answers. Within months, the full story will be known. And whether 3I Atlas proves to be a natural comet with exotic chemistry, or something that challenges our understanding, it will have taught humanity invaluable lessons about how the universe works. Every time Earth reaches perihelion each January, remember this: you're moving through space at over 67,000 miles per hour, following laws discovered 400 years ago, participating in the same cosmic dance that governs everything from the smallest satellites to the largest galaxies. Look up tonight if you have clear skies. Find Jupiter or Venus or Mars in the sky. Each of those worlds is experiencing its own perihelion passages, following the same physics, tracing elliptical paths determined by their energy and angular momentum. And between those visible planets, invisible to your eyes, interstellar wanderers are passing through, ancient voyagers from distant suns, each carrying stories billions of years old. The universe is vast, complex, and beautiful. But it's also knowable. The same laws that govern distant galaxies govern the motion of planets. Around our Sunday understanding, perihelion means understanding orbital mechanics, energy conservation, angular momentum, and the elegant simplicity underlying apparent complexity. That's the gift of science, not just facts and figures, but genuine understanding of how reality works at fundamental levels. So thank you for watching. Thank you for staying curious. Thank you for wanting to understand not just what happens, but why it happens. That curiosity, that desire to comprehend the universe through reason and evidence, is what makes us human. It's what drove Kepler to spend years calculating Mars's orbit by hand. It's what drives modern astronomers to spend cold nights at telescopes photographing faint comets. It's what brought you here to watch a deep dive into perihelion physics. If you found this video valuable, please share it with others who appreciate substantive science content. Click that subscribe button to stay updated as the 3i Atlas story develops. We'll be following the December observations and bringing you updates as scientists analyze the data. And most importantly, keep looking up, keep asking questions, keep seeking to understand. The cosmos is waiting, full of wonders like 3i Atlas, full of elegant physical laws like perihelion, full of mysteries waiting to be solved through careful observation and rigorous thinking. Clear skies, everyone. Until next time.